Okay, so last class we finished the BB84 protocol, and that was a huge milestone in quantum information, and it showed that one really important problem, that is the establishment of keys for the one-time pad protocol, could be done in a secure way using quantum systems, like qubits, the simplest system you can think of, the simplest quantum system you can think of. And you will eventually hear people say that quantum cryptography or quantum key distribution is perfect, is totally secure, you cannot hack it or anything, you cannot drop or anything. And those claims should be taken with caution, because it's not actually true that it's perfectly secure, because security is based on several assumptions regarding the experimental implementation of the of the protocol that are not uh, met in real life. So you, there is always uh, work for the hackers and the eavesdroppers. They can always try to find some error in the implementation or some thing that is wrong with the experiment and try to get information from there. But the thing is that if you could, in principle, implement it with perfection, then it will be secure. It is different from other cryptography protocols, classical cryptography, which are based on the hardness of some mathematical problems. So it brings something new, but it is not true that it's 100% secure. Okay, so that should be taken, those kind of uh, sentences, that those kinds of claims should be taken with caution. Okay, and another thing that happens is that, okay, so if quantum systems can help with that, maybe quantum systems can also help with other um, cryptography tests. And the other one I would like to talk about is bit commitment is also an important task in cryptography. And for us to understand, I will start with a simple problem. And that problem is you and your friend, who is very, very far from you, you're trying to uh, play head and tails, flip a coin, but you're not meeting each other. So uh, you have to flip a coin over the telephone. Okay. Just a minute. Okay. So um, how could we proceed if we want to flip a coin over the telephone without meeting that a person and uh, for doing that? Oh my God. Okay. So you could do the following thing. So again, uh, the two parties will be Alice and Bob, and they want to resolve some dispute using heads and tails by flipping a coin. And they are far apart, they are not meeting, so they have to do that over the telephone. So what they are going to use for that is a safe. So the safe they can send to each other for some way. And what Alice is going to do is she chooses heads or tails, write these in a piece of paper, and locks this piece of paper in the safe. She will send the safe to Bob, and she keeps the key. Okay, so she sends only the safe to Bob without the key. So in principle, Bob cannot open the safe. Bob will flip the coin and decide if you want what is the result, heads or tails. And he will phone Alice or send a message, whatever, Twitter or whatever, and he will tell Alice about the result. Okay, once Alice get that message, she will send the key to Bob, who will now open the safe and check the choice that Alice made in the beginning. And he will compare that with the outcome of his coin flip. So if the results coincide, if Alice's choice coincides with the outcome of Bob's coin flip, Alice's win and he loses. If the results do not coincide with Alice's choice and his coin flip do not coincide, he wins and Alice loses. Okay, so this in principle solves the problem, but despite the uh, technicalities of sending the message is easy, but the technicality of sending a safe or key or everything, there are other problems. And these problems made it impossible to do this in a secure way. So why is this impossible? Because regardless of what they do, at least one of two things can happen. Bob can use brute force and open the safe before. So instead of really flipping a coin, he could just break the safe, read Alice's choices, and write a message saying that the choices were different. Okay. Or depending on the protocol they use, the safe they use, Alice has some way of changing the content of the safe after the coin flip, after she gets the message Bob sent her with the result of the coin flip. So at least one of these things can happen. Either Bob can cheat by opening the safe by brute force, or Alice can cheat by changing the content of the safe after she learns what the outcome of Bob's coin flip. Okay, so there's no secure way of doing this with classical strategies, and this is discussed uh, on this reference here. So these references I'm putting here, some of them are really, really good. So if you're interested in this problem, I highly recommend that you take a look. Okay. And to formalize this a bit, this is a protocol that we call bit commitment. And this is I will not go into the details here, but this is a really, really, really important task in cryptography. We use it every day for like bank transfers and all of these things. So modern cryptography is built up on bit commitment, and current bit commitment protocols, they similar to other cryptography tests, they are done assuming the hardness of certain mathematical problems. For example, the hardness of um, factoring integers, really, really large integers. Okay? And again, this is a very nice review if you're interested. It's a nice paper to understand a bit about the problem. So it's basically flipping a coin over the telephone, but we just formalize it a bit. Okay. So quantum bit commitment protocol is divided into three stages. The first is the committing phase, in which Alice is going to commit to her choice of the bit. Okay, so it's the phase in which Alice makes a choice and puts that choice in the safe. So Alice will choose a bit, 0 or 1, and she will give a proof of that choice to Bob. Okay, that proof is what we call the safe in that other example we've seen before. And then they will wait until it's time for review the choice. This waiting phase, the length of this waiting phase will be decided by some use of the protocol. So it's not something that is necessarily the same every time you use the commitment protocol. But during the waiting phase, we need two things. First is what we call binding. Alice can change her mind after the first phase, so she cannot change the content of the safe. Once she logs her choice inside the safe, she cannot change her mind. And also, we need what we call concealing. Bob cannot find out what the value of B is until Alice decides to reveal it. So Bob cannot use brute force to break the safe and read what is inside. Okay. Then the third phase is what we call opening phase. So Alice reveals the value of B. So this is the part where Alice sends the key to Bob so he can open the safe and see what's inside. And the content of the safe is the evidence that Alice was telling the truth all the time. So Bob has the content of the safe is his security that she's telling the truth. And he will use that evidence to verify the accuracy of the information Alice is telling. Okay, so as I told you before, there is no way of doing this classically, but since the quantum system can help with other cryptography tasks like sharing keys, maybe it can also help with bit commitment, which would be really nice. So in the BB84 paper, which again is a really nice paper, I recommend that you read it, you will see that they propose one quantum bit commitment protocol, and it works like this. So again, they will use a qubit, and Alice will have to be able to prepare the qubit in the 4 different states, the same state that we use in the BB84 protocol. So if B is equal to 0, Alice will randomly prepare 0 or 1. So the only thing that the choice here say to us is that she's going to prepare from state that is an eigenvector of the D operator. It could be 0 or 1, and it is important that she chooses it random. So, and if her choice of the commitment is 1, Alice will prepare one of the eigenvectors of x plus or minus. Okay. The waiting phase, Alice will send this qubit to Bob. Again, we are imagining that they have a perfect quantum communication channel. So whatever she sends through the channel will arrive on Bob's end. Perfect. And again, we are assuming that Bob can measure in the x and basis in such a way that it's exactly what Alice and Bob are, what Alice is using as x and z base. Okay, so in the waiting phase, Alice, they do nothing, they just wait. And Alice sends the qubit to Bob, and Bob will keep this qubit until the revealing phase. Okay, so in the opening phase, Alice is just going to call Bob and tell him the value of B, 0 or 1. And she will also set what was the prepared state. If B is equal to 0, the prepared state would be 0 or 1. And she would tell Bob that it was 0 or 1. So she will call Bob, hey Bob, my choice was B equal to 0, and I think you state 0, or I think you state 1. And if B was equal to 1, she will say, I sent you plus or I sent you minus. Then Bob has the qubit with him, and this is the proof that she's telling the truth. So what he's going to do to verify that Alice is telling the truth? He will measure the qubit he has in the proper basis, X or Z. If Alice is telling the truth with 100% probability, he will get the associated outcome with that with the state Alice sent him. If Alice is not telling the truth, if she sends 0 and is telling that she chose B equal to 1, so she sends 0 and Bob is measuring X, he could get plus or minus with the same probability. So there is a chance that he will get her cheating. 50% chance of getting her cheating. And in this kind of protocol, we don't want to cheat if we can get caught. So if there is a chance that we will get caught, the protocol does not work. So Alice will only cheat if she is 100% that she will not get caught. So in this way, she will have to tell the truth, okay, in principle. So if they both act according to the protocol, especially Alice, it is very secure against Bob, the problem is against Alice. So if Alice acts according to the protocol, she cannot cheat by saying that she chose a different bit by the end. But it happens that there is a way in which she can cheat. We're not going to see it today because we need to learn a little bit more about entanglement, which we are going to do today in next class. In the BB84 original paper where they proposed this quantum decommitment protocol, they show that this protocol doesn't work because Alice can cheat using entanglement, as we're going to see next class probably, or next week, okay? And a few years later, there were 2 no-go results saying that it is impossible to devise perfectly safe quantum protocols for bit commitment. So today we still work on this because not perfect bit commitment is important. So we want the protocol to be as secure as possible, even if it's not perfect. So I have a project that's been running for several years now on this. It's not going to deliver completely safe protocol, but it can be better than classical ones. That's what we hope. Okay. So why I wanted to talk about it, about this protocol, because sometimes people will talk about quantum information, quantum computation, quantum cryptography as being the solution to all the problems in computer science, in cryptography, and this is not the case. There are things that quantum systems can help, but there are things that can actually, they continue being impossible with quantum systems as well. So whenever you have this really strong claim that something is perfect, something is unbreakable, something will solve all of the problems of humanity, we have to be really, really careful. And there are things that quantum technology might help, and there are things that quantum technology does not help at all. Okay. Okay, questions about this?